Hi everyone, in this video we will be having some more exercises regarding the concentrations of solutions. So we might be interconverting one unit of concentration to another and then find out some practical applications as well. Alright, so here in this first example we have an average adult human male has a total blood volume of 5.0 liters. If the concentration of sodium ion, which has a molar mass of 23 grams per mole, in this average individual is 0.135 molars, what is the mass of sodium ions circulating in the blood? Alright, so in here we are given 0.135 molars of sodium ion Na+, and then the volume, okay, for the number of liters for our solution, okay, is 5.0 liters. Then we also have the molar mass, which is 23 grams per mole. And we are asked how many grams or how much mass is there of sodium ions that are circulating in the blood. Okay, so for our solution, we take note that we know that molarity is the number of moles of solute, as in this case it is the sodium ions over liter solutions. Okay, so moles per liter, that's our molarity. But we are asked for the number of grams of sodium ion Na+. So what we can do is use the value of molarity. Okay, this one is already given, so we can just substitute. Then we have 0.135 molars is equal to, we do not know yet the moles, okay, x moles of Na+, but what we do have is the 5-liter solution that comprises this concentration. Okay, so this is 5.0 liter solution. Now take note that if we expand this one, if we expand m, that also is moles per liter solution, right? That's moles per liter solution practically. And so what are we going to do next? We have to find out moles of Na. All right, so for it to be clear, let me just write it down so that I can also show the cancellation of units. Right, so again, this is still part of the solution. 0.135 mole Na over liter solution, this is Na plus, is equal to x. Okay, we do not know this number of moles, x moles of Na plus, all over 5.0 L solution. Now what we can do is cross multiply so that we can find the value of x. So this is x L solution is equal to 0.135 moles Na plus times 5.0 liter solution. And then in here, we can see that liter solution appears on both sides. We only need to find x. So we can cancel. We can divide both equations by liter solution. And so in the same way here, we can divide this one there, right? So what we now have is the unit moles of Na plus. So our x is 0.135 moles of Na plus times 5, right? 5.0. So x here is 0.135 times 5 that is 0.67 or 675 moles. That's Na. However, we wanted to get the mass of Na. Okay, we are looking for the grams of Na plus. So what we can do now is to convert moles into grams, and so we will have grams of Na plus is equal to 0.675 moles. We use the molar mass of sodium. Okay, so we know that sodium has a molar mass of 23.0 grams, and this is 1 mole. So practically we are just multiplying it with the molar mass. So we can cancel moles. And here we have grams is equal to 0.675 times 23. You have 15, right? So imagine there are 15 grams of sodium ions circulating in the body. That's 15.5. In the problem, we have 2 least SF, so we can round this off into 16 grams. So that's 16 grams of Na. Okay? So imagine 16 grams of Na allowing electrical impulses for the nerves so that the nerves can communicate. Okay, that's 16 grams. All right, take time to take in the solution or the steps. So first we got the number of moles, okay, by clearly defining molarity, that's moles per liter solution, and we assign the number of moles as X. After that one, we change X into grams, okay, by using the molar mass. All right, our next example has something to do with interconverting using the density of the solvent. All right, so in here we are asked to calculate the molality of a solution that contains 51.2 grams of naphthalene. So this is 51.2 grams of C10H8, okay, which has a molar mass. Okay, if you try to check also the molar mass is already given 128.18 grams per mole. And then this is our solute, so let's assume that it is being dispersed in carbon tetrachloride, 500 mil of it. Okay, so another one is 500.0 mil of CCl4. Now the molar mass, this is 4, the molar mass of CCl4 is 153.81 grams per mole. And we are also given its density, okay? The density of which is 1.60 grams per mil. Okay, and later on we will know why density is given, okay, or is very much needed to solve this problem. Okay, remember that we are required the molality, small letter m, and we know that molality is just the number of moles of solute. Okay, if you review the concentrations, number of moles of solute over kilogram solvent. Okay, moles of solute per kilogram solvent. So for our solution, we can just go directly. Small m is equal to our solute is naphthalene C10H8, but we are given the unit of grams. So what we can do is convert 51.2 grams C10H8 into number of moles using the molar mass. All right, so we write 128.18 grams here, and then 1 mole C10 rather, H8. Now we can cancel the unit of grams so that we end up with moles, right? And then later on we will divide this. We will divide the whole term with a quantity that gives us the kilogram solvent. However, right now, what we do have is the volume of our solvent, which is 500.0 mil. All right. So we have 500.0 mil of CCl4. What we can do is use the density of carbon tetrachloride as a conversion factor such that we can cancel out mil and we end up with grams. All right. So again, we use this density to cancel out mil and end up with grams. So take note that when you say grams per mil, that is just basically 1.60 grams of CCl4 over 1 mil, okay, per mil man, per milliliters of CCl4. Now we can perform the cancellation, right? And what we do have right now is uh, 160 grams times 500 mil. However, we do not stop there yet because it actually asks for kilogram solvent. So in order for us to convert this into kilograms, we take note that 1000 grams is equal to 1 kilogram. Okay? And then we cancel here. All right. So if we do, you can do this directly on your calculator, just put it in. But if you want to have all numerators first divided by all denominators or the product of the digits in the denominators, then that could be also. All right. So let's have 51.2 divided by 128.18. Right. So you have an answer here which is equal to 0.3994 something, okay, 3994 and onwards. So that is our number of moles of naphthalene. We divide it with our answer for the denominator, this 500 times 1.60 divided by 1000. So you have 0.8 kilograms. And so therefore, if we divide 0.3994 divided by 0.8, we'll have an answer of 0.4992. And since we have three significant figures, okay, the given with the least number of SFs has 3 SFs, so we may end up with 0.499, okay, 0. Or that's almost equal to 5. So if you have answered 5, 0.5, then that's fine also, okay, very little differences. And then this should be moles per kilogram, moles of naphthalene per kilogram solvent, which is CCl4, or you can write this as kilogram CCl4. Or in short term, okay, short notation, you have 0.499 molal. Okay, 0.499 molal or small m. And that's our molality. So again, what did we do? We converted grams of our solute into the moles of solute and converted also the volume of our solvent into the kilogram solvent into mass using its density. Okay, we maximize the use of density. Okay, I'll give you a minute to take in the solutions or clarify what you haven't understood yet. So the next example is actually a sort of derivation, and then I deem it is very important for us to know this because if you've noticed when we are talking about limits or for example contamination limits in drinking water, if you look at a government document, it's actually reported as milligrams per liter solution. So mg per L solution. Okay, and that milligram per liter solution is just practically our parts per million. So in this item, let us prove that one part per million is equal to 1 milligram per liter solution. All right. So first, we must have an understanding of what parts per million is, and I'd like to take you back to percent as an analogy. Okay. So when you say 50%, okay. So this is an example. When you say 50%, that means 50 parts per 100, right? 50 parts per 100 parts, okay, or 100 total, okay? So the 100 here gives us the total number of the sample or total mass, total volume, whichever, all right? So in a way, when you say 50% by mass, when you say something is 50% by mass, M over M, then that means that is equivalent to 50 grams of solute in the case of solutions over 100 grams of your solution. All right. So that's practically how we visualize percentage. So if you have a pie here, which is 100%, the whole of the pie is 100%, then we say that 50% is in here. All right. So that is for percentage. However, for parts per million, okay, it is quite similar to uh, percentage, but however, the denominator there is actually 1 million. All right. So for example, if you have 2 parts per million, then that is a very trace amount. That is a very little amount compared to your solute or to the compared to your solvent rather. Okay, or compared to the volume of your solution. Then that means so if it's in grams, so that is just 2 parts over instead of 100 now. This is 1 million parts. All right, total. So this is now your total. Okay, or we could write this as 2 parts over 1 times 10 to the 6 parts, right? So 1 times 10 to the 6 there means our whole system, okay? It's the scientific notation for 1 million. So how do we prove that 1 ppm is equal to 1 milligram per liter solution? All right. So we take note that 1 ppm is equal to in terms of solutes and solution, we know that 1 ppm tells us that it's 1 gram over 1 gram of solute over 100 grams, or 1 million rather, 1 million, 1 times 10 to the 6 grams of the solution of the whole thing already. Okay, that means solution plus solute, solution plus solvent, or solute plus solvent. Then what we can do is convert this one, okay, we know that 1 gram, okay, again, we are proving that this quantity is equal to 1 milligram per liter solution. So first, we can convert grams of solute into milligrams of solute. So we add another conversion factor wherein we know that 1, 1 milligram is equal to 1 gram of solute. 1000 milligram is equal to 1 gram of solute. Okay, so now we can cancel. Now we have milligrams of solute. This is solute. All right, so we are done with this. Now the thing here is we need to convert grams of solution to waters to uh, 1000 grams also, or to the liter solution. Okay, so we have to add another conversion factor. Okay, so in aqueous solutions, the solvent there is water. All right. So if the solvent there is water, at 4 degrees Celsius, the density of water is 1 gram per ml. Okay. Density of water is 1 gram H2O, 1 gram per ml of water. So if you convert that into 1,000 grams and you want to convert this ml to liters, then we know that the relationship is 1,000 grams of water of H2O is to how many mil or how many liter? 1. All right, so 1,000 ml. So this now translates into our conversion factor needed in here. All right, so that we can have 1,000 grams of water is to 1 liter of H2O. Then we can cancel, and we don't cancel liters H2O, but we can cancel grams of H2O. All right, in here. So gram solution also. Now we have 1 liter solution. So what we can do is combine everything. This is now Mg solute over liter solution. As for this case, since H2O is much greater in amount, then we can actually get the volume of the solvent as the volume of the solution itself already. All right. And so what we can do is multiply everything in the numerator and also in the denominator. So this is 1,000 times 1,000. Okay, that's 1 million. Then divide it with everything in the denominator. 1 exponent 6 is practically 1 million. Okay, and then times 1, therefore here 1 part per million is equal to 1 milligram solute over liter solution. So now we have this relationship. All right. So again, what we did was we translated parts per million as to 1 gram per 1 million of the solution. As for this case, we treated the solution or the mass of the solution to be that of water, since this is very great in amount, okay, much greater than the solute. We can already assume that the volume of the whole solution is contributed by the volume of water as the solvent. Okay, and then we converted grams into milligrams. Okay, and then after that one we converted grams of water or grams of solution by using the density of water, okay, for aqueous systems. So we now have 1 ppm is equal to 1 milligram per liter solution. Okay, or in some textbooks they can have 1 liter of water, which is fine as well. Again, the volume of the solution is contributed very much by water. All right, so a few minutes to absorb what has been discussed, and then we'll go into a practical example for this. So, as an application of the relationship, let's say we have this kind of problem. You have a water sample with 150 parts per million of dissolved lead 2 plus. All right, and then we take note that the molar mass of lead 2 plus is 207.2 grams per mole. All right, so because we have the relationship 1 ppm is equal to 1 milligrams per liter solution, then we can actually ask for another type of concentration, which is molarity. So in here, in this problem, you are given 150 ppm of dissolved lead 2 plus. What is this concentration expressed in molarity? All right. So how do we do this? We know that to get the molarity, it is moles of solute. As for this case, it's moles of Pb2 plus over liter solution. But what we do have is the parts per million. Okay, and so that means we have to convert first moles of lead, or we convert first grams of lead into moles of lead. So we start with M is equal to uh, again 150 ppm of lead 2 plus is equal to 150 milligrams Pb2 plus per liter solution. Okay, because of this relationship. Okay, so we can just directly write ppm as milligrams per liter solution. So in getting the molarity, we have this 150 milligrams of lead mgPb2 plus over 1 liter solution. Okay, so I'm just writing 1 to be consistent here. So this is now our ppm, the ppm quantity, the parts per million, okay, which we base from here. And since we wanted to have the molarity, we need to cancel out milligrams of lead first. Okay, so we know that 1000 milligrams Pb2 plus is equal to 1 gram of Pb2 plus. Then we can cancel, okay? 1000 milligram is to 1 gram. After that one, we can cancel grams of lead and convert it into moles. And what do we use? What conversion factor do we use? Okay, the molar mass. Okay, so 1 mole of lead 2 plus is equal to 207.2 grams of lead 2 plus. Now we can cancel grams of lead, cancel grams of lead. So we are left with moles of lead 2 plus, and you might have noticed that there isn't any change in the denominator, liter solution. Okay, so we let it stay as it is because after all, molarity is moles per liter solution. All right, so if we solve it completely, we have 150 divided by 1000, okay, divided by 207.2. Okay, or you can multiply all numerators first and divide it with the product of all the denominators. That works the same way too. So you can have 7.239 something 2393 times 10 to the negative 4 uh, moles lead or Pb2 plus per liter solution. Okay, so notice how we just write per liter solution, or we have two significant figures, so practically we are going to answer in 7.2 times 10 to the negative 4, and then mole lead over liter solution is m, okay, molars of Pb2 plus. All right. Now, what is a practical application for this one? Take note that if you are going to assess water quality, each contaminant, each metal, okay, or each undesired species must have an allowable limit, okay, must not exceed an allowable limit so that it will not be considered a pollutant. All right. So, for example, if the allowable limit for lead 2 plus in drinking water is 0.5, uh, 0.5 ppm, then it must not exceed 0.5 ppm. Okay. Otherwise, there will be some problems associated if that water is drunk or ingested, because they will also be having this ion. Okay, and take note that lead 2 plus is can cause brain damages. Okay, or it can be deposited in the tissues of the body. All right, so that's why we take a look at certain allowable limits for bodies of water, especially those that come from the faucet. All right, so that ends the exercises for this video. I hope you learned something. So right now you can take a break and then have your coffee or do a little stretching or some push-ups or crunches, whatever you want. Okay, so have a nice day.